now. And again, we're into chapter 15. And like I said, in 15 and 16, we're not going to perhaps talk about every single thing that's in there. We're just going to kind of touch upon some stuff along the way. So first off, lipids are biomolecules. They contain fatty acids or a steroid nucleus, which we'll kind of take a look at what those are in just a second. They're soluble in organic solvents, and they're named as sort of fats. They're extracted from cells using organic solvents. They're part of like cell membranes and stuff of that nature. Now, there's different types of lipids, and we're going to talk about some of these along the way. There's waxes, there's fats and oils. There's ones that are referred to as glycerol phospholipids. There's also prostaglandins, and there's steroids. Steroids is not technically they don't really contain a fatty acid. It has its own sort of look to it that we'll see in this chapter here. This next slide is a nice little slide about sort of the different things that we're going to talk about. And really kind of looking back, you kind of will need to know some of these parts here. Pretty much on here is a nice little slide that kind of tells you everything that's going on. And again, we're going to talk about each of these individually as we go through. But these are the main components of each of these different types of lipids. And again, referring back to this slide is probably a good slide to sort of understand the different parts of it. We'll see each of these individually as we go through, obviously, as well. So let's first talk about a fatty acid and sort of what fatty acids are. So fatty acids really are these really long chains of carbons and hydrogens. And at the end of these really long chains of carbons and hydrogens, you usually have some type of like carboxylic acid type group happening. So a fatty acid, again, just this really long chain. I won't draw a bunch of them, but long chain happening here, maybe 12 to 18 carbons long. Again, attached to these guys are nothing but hydrogens. And at the one end of it, or the other end, you have really a carboxylic acid type group here. So it usually has sort of a non-polar part here, right? These are all kind of carbons and hydrogens, and it's got sort of a polar part that's happening over here where the carboxylic acid is. They are insoluble in water, really because they're very long chains of carbons and hydrogens together. So you got this really long chain of non-polar that tries to interact with something like water, and it doesn't really interact really well. They could also be saturated or unsaturated, and that pretty much is the same definition as what we talked about in organic chemistry. Saturated means all carbon-carbon single bonds. Unsaturated means somewhere along the way you got at least one carbon-carbon double bond. So very much like what we talked about in sort of organic chemistry as well. So fatty acid formulas can be drawn very much like organic chemistry. So we could do sort of a condensed formula where the COOH, remember when we see something like this, that's our carboxylic acid group. So that is what it represents. So this is a condensed one. Also remember that we can sort of do this little shorthand here where we have repeatable units. So that means that there's 6 of these CH2 units just repeating one after each other. And that's important because a lot of times in fatty acids, you have to count the number of carbons. So if we were to count the carbons here, this would be 1 carbon, and then there would be actually 6 carbons here because they repeat 6 times. That's 7, and 1 more would be 8 carbons. So again, remember that you see that little parentheses. That means that that unit just keeps repeating. Here's our line structure, just like in organic chemistry. Again, each of these guys obviously are carbons, just like we draw it in organic as well. And again, our carboxylic acid group found here. Now, when we have saturated fatty acids, that again means that they have all of the single bonds. So they have all carbon-carbon single bonds. And because of that, what ends up happening is they really do sit together very nicely. And what that means is, as you can kind of see in this picture, our nonpolar part, they sit together really nicely. They fit pretty nice to each other. They're going to use some of those dispersion forces and interact really well. And what that means is they typically will have very high melting points, and they typically are solids at room temperature. Hence the steak, and the fat on the steak there is a result of saturated fatty acids. So because they are saturated, because they are all single bonded, they fit very nicely against each other when they come together. And typically saturated fatty acids, again, are going to be more solid at room temperature. And here's a table of that. And again, if you look at this table, they are all single bonded. So these are all saturated fatty acids. Again, it means they have all carbon-carbon single bonds, and they have the maximum number of hydrogens. Another way that we sometimes can classify fatty acids is by the number of carbons and the number of double bonds. So the number of carbons and the number of double bonds. So for example, this first guy here, if you count up all the carbons, as it says there, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, that would have 10 carbons and no double bonds. This is sometimes referred to as a 10 to 0 fatty acid, which means it has 10 carbons and no double bonds. The guy on the bottom here or near here has 18. So if you count up all the carbons in this guy, he's got 18 carbons and also no double bonds. This would be referred to as an 18 to 0 fatty acid. Again, 18 being the number of carbons, 0 being the number of double bonds. So that's a very common way that fatty acids are referred to: number of carbons, number of double bonds. If I had an 18 to 1 fatty acid, that would mean I have 18 carbons and one of those is a double bond. So that's a super very common way fatty acids are sort of referred to each other that way. Now we also have unsaturated fatty acids. So unsaturated fatty acids means that it does have a double bond somewhere. The consequence of that double bond is it makes a kink in the chain, as you can see here. And we do get cis and trans fatty acids, as we'll talk about from that. And it's the same thing as what we talked about in organic. Cis meaning same side double bond, trans meaning opposite sides of the double bond. And that's what we get, cis or trans fatty acids. But the main consequence, as I pointed here with the arrows, is it creates these sort of kinks in the chain. And what that's going to do is when we get a bunch of these sort of unsaturated fatty acids together, unlike saturated fatty acids, which sit really nicely together, because of these kinks that are in these chains, they no longer are able to sit really nice with each other. And they're not really able to pack together very tightly because of that. So as you can see, these chains are definitely not able to really fit very nicely together like we saw with our saturated fatty acids. The result of that is our saturated fatty acids that fit very nice together typically are solids at room temperature. These guys are typically liquids at room temperature. Again, they're not able to really get themselves tight to each other and maintain a very tight interaction with one another. And again, we end up with something that is more of a liquid. And again, that's different than our saturated, where I'll do my best to draw here. We have these really nicely fitting together chains because they're all single bonded, and we end up with more of a solid at room temperature because they do fit together very nicely, as opposed to down here where we get a lot of kinking that's occurring. And here's a table, and you have a similar table, I think, in your book of some different unsaturated fatty acids. But again, we do see at least one double bond here, a double bond here, a couple of double bonds happening here. And we could classify unsaturated fatty acids the same way. They were nice enough to count up the carbons. That's 16. And I believe there is one double bond there. So this would be referred to as a 16 to 1 fatty acid. Again, 16 meaning the number of carbons, 1 meaning the number of double bonds. I believe that says 18. So this would be classified as an 18 to 1 fatty acid. Now, if you had two like we do down here, this also has 18 carbons, but two double bonds. This guy would be referred to as an 18 to 2 fatty acid. Again, 18 being the number of carbons, and obviously 2 being the number of double bonds that are there. We also see the melting point is a lot less, and it gets even smaller as we keep slapping on those double bonds. So this guy's got like 4-ish double bonds, and we see it has the lowest melting point, and lower the melting point, the more chance it's going to melt easier and be a liquid. So again, the more double bonds you have in there, the more kinking you're going to get of those chains, and they're definitely not going to be able to sit very well together. Any questions on that there? And again, here's just some comparison. We see our melting points here are fairly high. And these are all guys that have no double bonds. And we expect them all to be more of a solid. Here we got at least 1, 2, 3 double bonds in these guys. These are unsaturated. And we can see a very big sort of decrease in our melting point temperatures when we look at those guys. And again, that is a result of our obviously double bonds that are there. So if we wanted to assign these different melting points to these different fatty acids, we can make a pretty educated guess. First off, we have an 18 carbon saturated, which is an 18 to 0 fatty acid. We have an 18 carbon with 1 double bond, which is an 18 to 1 fatty acid, and 18 carbons with 2 double bonds. So the one that's going to have the highest melting point and be the solid should be this guy here. So he should get the 69. Again, he has no double bond, so he's going to sit really nicely. That's going to result in pretty tight and good interaction, and that's going to cause the melting point to increase. Because remember, the stronger the intermolecular forces, the stronger the way they're able to interact with each other, the higher things like melting points are and boiling points, just like what we saw in organic chemistry. Now, these both are unsaturated, but this guy on the bottom has the most unsaturation, which means for every one of him, you're going to get a couple of probably kinking to occur in that chain, and he should end up with probably the lowest melting point, minus 17. And that would leave, obviously, this guy in the middle with 13. Again, lower than our saturated, but a little bit higher than our doubly unsaturated, as we see there with our two double bonds. Any questions on that there? Okay. So let's talk a little bit about prostaglandins. Prostaglandins are 20 carbons, atoms in their fatty acids. They got some OH groups at carbons 11 and 15, not truly important for us. They have the trans double bond. Prostaglandins are basically produced as a result of injury. So like here, which is probably not recommended to hammer your thumb there. If you hammer your thumb, you're going to start to produce this. It's involved in what we obviously have for pain and inflammation. And we could take something, maybe some Tylenol or aspirin. And what that does is it tries to block the formation of our prostaglandins, and you hopefully feel a little bit better at that point as a result of inflammation there that occurs. So prostaglandin is kind of really a fatty acid. It has a pretty long chain, and again, has a trans sort of bond that's happening there. Again, basically produced as a result of injury or inflammation there in the body. Another very common sort of fatty acid that we hear a lot about is omega-6 and omega-3 fatty acids. And that is basically what omega-6 fatty acids are. It means that the first double bond that we see occurs at carbon number 6, hence the omega-6. Omega-3 means that the first double bond that we see occurs at carbon number 3. Now, when we're counting this is actually different than a lot of things that we do normally in organic chemistry, where this group would be which is at the end here on both of these. This is normally where we would actually classify as carbon number 1. But when we're counting for like omega-6 or omega-3 fatty acids, we actually start counting at the opposite side. And if we do that, that would be carbon 1, and this would be carbon 2, 3, 4, 5, and then 6 would be right there. Again, remember there's 4 carbons here, plus 1 is 5. The next guy would be 6, and that would be linolenic acid, and that is our omega-6 fatty acid, where we see our first double bond occur. Again, different as well. We start counting on the opposite side here, and this is carbon 1, this is carbon 2, and then this is carbon 3, where we see our first double bond occurring. So these guys are found in vegetable oils and fish oils and can have some pretty good properties. It's been found. But again, in this one instance, probably the only one we've talked about, we actually start numbering or counting from the opposite side of our sort of organic functional group over here, our carboxylic acid. So that's an unusual sort of thing. Any questions on that there? And here's a few more examples of omega-6 and omega-3 fatty acids. Again, starting to count on the opposite end, as we just saw there. First double bond at carbon 6, second one here, double bond at carbon 3. And again, this would be carbon 1, 2, and 3 in this case. 1, 2, and 3 as well. Again, counting in that direction here for omega-3 and omega-6 fatty acids. Write out a saturated acid with 10 fatty acid with 10 carbons that is saturated mono unsaturated omega-3 and mono unsaturated omega-6. So we'll just kind of look at those pictures here. I think we have them. So saturated basically means that we have all single bonds, and obviously 10 carbons would be counting starting. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, mono unsaturated means basically one double bond. Omega-3 would be our third carbon. Again, counting at the opposite direction of our carbon carboxyl group there. So starting here, carbon 1, carbon 2, and carbon 3 would be our omega-3. And mono unsaturated also means only one double bond. And omega-6 means starting again, counting opposite side, 1, 2, 3, 4, 5, and 6, where we see our first double bond happening. So that's what those guys would look like. That's more of a condensed structure. Again, sort of line structure, which is how they are commonly drawn. I wasn't even keeping track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Went way too over on that. So, oops. Something like this. Again, would look something like what we got going on in sort of line structure. Any questions on what they look like? I don't know if you'll be asked to draw them, but you, again, may be given a formula and you need to be able to recognize it definitely as either omega-3 or omega-6. You also need to be able to recognize it again as an 18-to-1, 18-to-2, 18-to-0 fatty acid. And you need to know the general structure of a fatty acid, which is, again, non-polar carbons and hydrogens, carboxylic acid group at the end of it. Any questions in terms of fatty acids, which you need to kind of know? Okay, then let's talk about waxes a little bit and fats and oils. So waxes are esters of saturated fatty acids and long chain alcohols. And basically this is our ester bond right here. Remember that our ester bond is made out from basically a carboxylic acid plus an alcohol, right? And basically we're going to take out water, right? So we're going to remove water. And when we do, we get our ester bond that forms, which is what we see here. So waxes are basically this. It's basically a long alcohol that has a lot of carbons attached to it, and a long chain, really fatty acid, which is basically a long chain carboxylic acid that comes together to make some different types of waxes that you're probably familiar with. There's beeswax, carnauba wax as well. Now, fats and oils are sometimes referred to as triacylglycerols, also sometimes referred to as TAG, it used to be, for triacylglycerol. And they are produced by the esterification reaction, and that esterification reaction is the same one that we talked about in organic chemistry. It's the one I just pretty much drew there. It is our carboxylic acid again with sort of an alcohol group taking out our water and making that ester bond that basically forms. And here's an example of that in a triacylglycerol. Glycerol forms an ester bond. So this is glycerol. You should be familiar with what glycerol looks like. Again, probably will not be asked to draw it, but if you see the picture of it, you should be familiar with it. It is a 3-carbon substance. It has 1, 2, 3 OH groups on it. And again, that's kind of like the alcohol part of it that's going to be attached to our carboxylic acid part and make up our 3 ester bonds that happen right about there. Again, that's a result of this glycerol and our fatty acid that has our carboxylic acid group on it. Just make a scribble. And again, taking out the OH and the H and binding it together. So for a triacylglycerol, this is an important little picture here. It is made up of, and this is what you need to know, it is made up of a glycerol unit and 3 fatty acids. So 1 glycerol and 3 fatty acids makes up a triacylglycerol. They are held together by ester bonds, 3 ester bonds in that case. Any questions on that there? So here again is that formation, taking out water, as you can see in the box here. And really nothing changes, just kind of squish everybody together. And we get this triacylglycerol here with our ester bond sort of happening, 1, 2, and 3 of them. Again, you won't be asked to draw this, but you should know that, again, triacylglycerol is made up of a glycerol unit, 3 fatty acids, and you should be recognized the bond as an ester bond. Now, olive oil contains a really high percentage of this type of acid, and it is mono unsaturated fatty acid. So what we see here is what we talked about. This is our glycerol unit. These are our 1, 2, and 3 fatty acids that's attached here in sort of olive oil. Because it has the double bond action happening here, they're not going to sit very nice with each other here. And as we know, olive oil is more of a liquid under normal conditions. And it's because of the fatty acid part here and those double bonds that are present that's not going to let it really sit really tightly to each other. We don't have to worry about that. We're not going to talk about naming any type of fatty acids or anything like that, so you don't have to worry about that. So as I talked about, and really sort of relatable to what we were talking about in terms of fatty acids, typically these triacylglycerols is a fat. It will be a solid at room temperature. And again, those are guys that pretty much have saturated fatty acids, so they'll sit really nicely. And those that will be an oil will typically be liquids at room temperature. So things like olive oil and so forth, like we just saw there, are very common examples of that. So the more unsaturation you have, the more chance you're going to have sort of an oil or a liquid at room temperature. And again, that's a result of those fatty acid part of the chain really not sitting tight to each other. So you don't have a lot of intermolecular forces holding very tightly. So they're very easily sort of moved apart from each other, if you will. And again, have a lower melting point and also a liquid at room temperature. Again, as we can see here with our olive oil example. We'll skip that. That's not important. Some properties of triacylglycerol. They actually undergo the exact same reactions as, alkenes, really, because a lot of them, have these double bonds. So they can undergo similar types of reactions. One is a hydrogenation, and that's how we get certain foods that we sometimes hear about, right? This thing is partially hydrogenated. That's basically what we're talking about here. We're basically going to be adding hydrogens. So hydrogenation means we add hydrogens, and essentially just like it was in that basic organic reaction where you had a double bond and you added 2 hydrogens or H2 to it, pretty much the double bond just became a single bond. And that's essentially what happens with our triacylglycerols, and you do a hydrogenation reaction. Basically, the H2 finds those double bonds and makes them a single bond. The result of that is your fatty acid part of it now will be more single bonded, which should then allow a lot of these guys to kind of sit together a little bit better. And, that's how we go from, say, something like oils to, say, something like margarine, right? It's a little bit solider, right, when you have margarine than, say, oil. And it's because it's partially hydrogenated. We got rid of a lot of the double bonds. Because you got rid of double bonds, it's going to become more of a solid at room temperature. You might not get rid of all of the double bonds, which is why it's not like a rock hard solid. But get rid of some of the double bonds, it actually goes more from a liquid like an oil to, say, something like margarine or something like that, which is obviously solid, right? But, a little bit liquidy, but more so solid than obviously an oil. It could also go through hydrolysis, which is essentially just splitting it back apart. So if we have a triacylglycerol, we have that ester bond. And by adding water, we could break it back apart and really kind of regenerate our carboxylic acid part on the fatty acid and our long chain alcohol back. So that's a very similar sort of reaction that we saw in organic chemistry that also sort of happens here. So hydrogenation of oils converts some, or if not all, but a good portion of the double bonds that we see in these triacylglycerols into single bonds, going to allow it to pack a lot better and go from, again, a more liquid like we see here to something more solid like we see over here. And again, that's how we produce things like margarine or shortening in that particular case. So how's that reaction work? It is identical to an organic one. Again, even though it looks maybe a little bit more scary, this thing is ginormous, but it's really like the organic stuff we talked about, only going to attack one location. And it's only going to attack the double bond in each of those locations. And there is 1, 2, and 3 double bonds, which is why we added not 1 H2, but 3 H2s, 1 for each of the double bonds that are there. And basically everything else in this entire giant thing will remain the same, except that we will convert those double bonds into a single bond. The nickel that's there is basically just there as a catalyst to help speed up this reaction and make sure that it occurs a lot faster than it normally would. So not really participating in anything. It's just acting as a catalyst here. Any questions on that? Again, I don't anticipate you need to draw this, but you should have in your head sort of what happens in this type of reaction. So again, it's very identical to what we talked about in organic chemistry. When you add H2 to a double bond, the double bond basically becomes a single bond. The consequence of that in terms of these triacylglycerols is we're going to go from something that is, again, more of a liquid to something that's going to become more solid in the state of that. Any questions on that there? We're going to skip this because we're not going to talk about naming any of these things, so you don't have to worry about naming them. Lester, I think, has been off the market for a long time, so we'll skip that as well. But a consequence, though, of sort of this process of hydrogenation is in this process, we do end up getting some different unsaturated fatty acids that can develop, or just in general, there's different unsaturated fatty acids. And again, we have our cis and our trans. So just like it was in organic, cis meaning same side, trans meaning opposite side. So here our bulky group by the double bond is on the same side. So this would be a cis fatty acid, while our bulky group here, which is just the long carbon groups, are on opposite sides of the double bond, and that would be our trans. So this bottom guy here would be referred to as a trans fatty acid. Top guy would be referred to as a cis fatty acid. Now, like I said, some of the problems with perhaps the hydrogenation reaction is sometimes during that process of hydrogenation, we can convert some of the cis double bonds into trans double bonds. And trans double bonds are trans fatty acids in our body, behaves just like saturated fatty acids. And they were estimated to make up about 2 to 4% of our total daily calories. This slide's relatively old, so that's a while ago. They've actually, as of a lot of number of years at this point, have tried to eliminate a lot of trans fatty acids, especially maybe about 5 or 6 years ago. You heard like everybody's using different sort of oils and stuff like that in cooking at restaurants to eliminate the use of trans fatty acids. And really the reason why that is because there's a lot of studies that showed that by consuming trans fatty acids, it would raise people's LDL cholesterol and actually lower their HDL cholesterol. If you're not familiar with LDL cholesterol, is the bad cholesterol. Somebody once said you could remember that by L for lousy. So that's the lousy cholesterol. HDL is heavenly. That's the good stuff. So they had a lot of studies that sort of showed that consuming trans fatty acids actually raised your bad cholesterol and kind of lowered your good one, which obviously not a great situation in that particular case. A lot of places now, I don't think even use it anymore. Like I said, maybe, I almost want to say maybe 5 or even maybe longer by now, 8 years ago, there was a big sort of push to eliminate, the kind of the use of trans fatty acids in a lot of places. All right, so some of these true and false ones here. There are more unsaturated fatty acids in vegetable oils. That is true. So unsaturated means double bonds. Double bonds means it's going to be more of a liquid, so that makes sense. Vegetable oils have higher melting points than fats, and that's going to be false. Fats, which are solids, which are saturated fatty acids, have all single bonds, so they're going to be fitting tighter and have a higher melting point. Hydrogenation converts some cis to trans. That is true, as we just talked about. And animal fats have more saturated fat. Again, all those single bonds going to allow it to sit together and be more solid at room temperature. Any questions on that there? So another reaction, as we talked about here, that triacylglycerols go through our hydrolysis reaction. Hydrolysis really just means that we're going to add water and we're going to basically split this guy back apart. So we're essentially going to break our ester bond here. And we have, again, 1 bond to break, 2 bonds to break, 3 bonds to break. And that is why we're adding 3 waters in this case. Again, when we break that apart, you could kind of just assume an H goes on this side, an OH goes on the other side, and we get a completed glycerol unit back and our completed carboxylic acid group back, all 3 of them in this particular case. So hydrolysis basically will break apart our triacylglycerol and basically get back the components of a triacylglycerol, which is a completed glycerol unit and 3 fatty acids. So we get our glycerol back and our 3 fatty acids. Any questions on that? Again, not going to be asked to draw that, but you should have an understanding of what sort of happens if you add, say, water or do a hydrolysis reaction to a triacylglycerol. Any questions on that? This is also how we sort of make soap, but instead of using, say, excuse me, instead of using water, we use something like a base, and it breaks apart very similar. But because we're not using water, kind of like what we talked about in organic chemistry, we don't have enough parts, if you will, to put back everybody. We have enough to get back the glycerol. Again, we would break it here. So if you just think about it, we can put our OH back, our H back on there into each of those to get our OHs. But then we can only put an O on here. And what that gives us is basically soap. So soap, as we I think maybe have talked about before, has a non-polar part. And then it ends up with this polar part here. So that is the polar part, the polar head of soap. This is the non-polar tail of soap. And I think we might have talked about it, but just kind of a review of it. Dirt is typically non-polar, so basically soap and that non-polar tail with all the carbons and hydrogens, that is what my bad squiggly line should represent, basically will surround the dirt because they will mix really well, dispersion forces and dispersion forces. And on the outside, you have basically your polar part, and that's good because then you come with water and you wash away the soap. So essentially the soap traps all the dirt inside. It allows the outside basically that likes water to be out there. And basically when you wash it away, there goes your dirt along with your soap. Any questions on that? That's sometimes referred to as a micelle, how it kind of traps everything together, a bunch of soap molecules around the dirt, wash it off with water. All right. Again, you don't have to worry about any of these since we're not really remembering any names or anything of these guys. We'll kind of skip through these so you don't have to worry about it. It's a good lecture. All right. So let's talk about another type of lipid, which is sometimes referred to as a glycerol phospholipid. So a triacylglycerol has a glycerol unit and 3 fatty acids. A glycerol phospholipid, which is found in cell membranes, also has that glycerol unit. It has 2 fatty acids. It has a phosphate. And it has an amino alcohol. And we'll see some amino alcohols in just a second. But a very popular one is choline, is an example of an amino alcohol. So you do need to know this one here, the parts here of a glycerol phospholipid, again, made up of a glycerol unit, 2 fatty acids, a phosphate, and an amino alcohol. So kind of, again, what's on this slide, it's important to sort of know. They are polar. They have 2 non-polar fatty acid chains. They have a phosphate group and an amino alcohol. And here's some examples of amino alcohols. And again, choline is an example of it. And it has this sort of polar part. Again, you see the positive nitrogen in each of those, creating a polar side to that molecule. So when we look at a glycerol phospholipid, it also has sort of 2 parts to it, if you will. Again, this is our fatty acids back here. So that's our fatty acid chain. This is basically our glycerol unit. This is our phosphate here. This is our amino alcohol. And kind of like soap, it also has 2 parts to it. So where our fatty acid part is the nonpolar tail of it, and where our amino alcohol is is the polar head. So you need to recognize that in a glycerophospholipid, the fatty acids represent the non-polar tail of sort of our membrane, and the amino alcohol part where the phosphate group is as well is our polar head part. And again, it can act very well that way. It has a part that likes water, which is the polar part. It has a part that doesn't like water, which is the non-polar part. Any questions on that? So again, the sort of general structure here of glycerophospholipids having, again, a glycerol unit, 2 fatty acids, a phosphate group, and an amino alcohol are things that you should know. Any questions on that? Another type of lipid is one that is referred to as a sphingolipid. I can never say this word correctly, I'm sure. They are similar to phospholipids, but they contain sphingosine, which is a long chain amino alcohol, and it also has a fatty acid, a phosphate group as well. So instead of glycerol, this guy has this guy right here, which is sphingosine. We'll see a picture of it in just a second. It also contains a fatty acid. It has 1 fatty acid, a phosphate group, and again, an amino alcohol, just like choline or something like that. Just like the other one, this is going to be more of our non-polar part where our fatty acid is. This is going to be our more polar part of this guy. Just like the other ones there, the triacylglycerol and the glycerophospholipid. What's on this slide, you need to know the components of this type of lipid here, the sphingolipid. Any questions on that? Here's what that guy looks like. Again, kind of similar to glycerol. Does have sort of a 3-carbon run, but it's got some other stuff attached there that's different than glycerol. Glycerol is all OH groups, but as you can see here, it has NH2 on it instead, a nitrogen-containing group that happens there. Here's an example of a sphingolipid. This is sphingomelanin, which is found in nerve cells. I apologize for the butchering of the names here. And it has an amide bond between the fatty acid and our sort of backbone here. And this is our fatty acid here, and this is our amide bond. So if you remember from organic, our amide bond is carbon, oxygen, and attached to a nitrogen. So that's our amide bond that actually happens here. So again, this whole part here is our kind of sphingosine. There's our fatty acid. This is our phosphate right here. And again, choline, which is an amino alcohol attached there. Any questions on that? So for sphingolipids, you need to know, again, the components that make it up. Sphingosine, 1 fatty acid, phosphate group, and amino alcohol. Any questions on that? Lastly, in terms of something that's maybe not necessarily a lipid, as it doesn't have necessary fatty acids, is a steroid nucleus. And what we see here to the right is a steroid nucleus. Is kind of made up of basically 2, 3 cyclohexane type rings like we see in organic chemistry, and 1 cyclopentane ring here, just like what we see in organic chemistry, all sort of hooked together. No long chain fatty acids basically attached here. An example of something that's sort of a steroid is cholesterol. And again, you could see the steroid nucleus right here, made up of those 3 cyclohexane rings and 1 cyclopentane ring. What you need to know about this is you need to be able to recognize this as the steroid nucleus. Any questions on that? Obviously, you will not be asked to draw it, but if the picture is given to you, you need to be able to recognize that part of it as being a steroid and that being a steroid nucleus. Any questions on that? Okay, believe it or not, that is chapter 15. So again, from chapter 15, you need to know fatty acids, what they are made of, the components of what it looks like. You need to be able to classify fatty acids by the number of carbons and the number of double bonds. You obviously need to know what an unsaturated and saturated fatty acid is. You need to know that a triacylglycerol is made up of a glycerol unit and 3 fatty acids. You need to know that a glycerol phospholipid is made up of a glycerol unit, 2 fatty acids, a phosphate group, and a amino alcohol. You need to know that a sphingolipid is made up of sphingosine, a fatty acid, a phosphate group, and a what we got there, amino alcohol. And you need to be able to recognize the steroid nucleus. Any questions on, obviously, what we talked about in terms of hydrogenation reactions? You need to be able to recognize what happens in those. Any questions on what you need to know from chapter 15? Okay. Then might as well keep rolling to chapter 16. And again, we're not going to cover everything that's in chapter 16. We'll hit on some important parts here to finish it up. So we're going to talk a little bit about proteins and amino acids. So obviously, proteins provide a lot of different sort of functions. There's structural proteins, there's transport proteins, there's storage proteins. There's some are hormones and protective type proteins, but pretty much all proteins are made up of amino acids, and amino acids are basically the building blocks of proteins. So the first thing that you need to know, obviously, is amino acids are the building blocks of proteins, but you need to know sort of the general structure of an amino acid, and that is what we see on the bottom here. So you do need to know this general structure. A general structure of an amino acid is a carbon. It has a carboxylic acid group. It has basically an amine group here, a nitrogen group. It has a hydrogen, and it has an R. And R is what is referred to as a side group. And all amino acids pretty much have this part always. And what makes them different amino acids, there's like 20 of them. What makes them different amino acids is really what's attached here. So depending on what group it's attached there, will give you a different amino acid. This is what is referred to as the non-ionized form. This is what is sometimes referred to as the ionized form. This is also an amino acid. This is, again, the basic unit of an amino acid. The difference is we put an H plus over here, and we took the H plus off of here. So we get sort of an ionized version of it, a positive side and a negative side. This is also sometimes referred to as the Zitteron ion version of it, where we have that group basically there. Any questions on that? So first off, you do need to know the general sort of structure of an amino acid. Again, probably will not be asked to draw it, but if you see it, you need to be able to recognize it, obviously. Here are some amino acids. You will not need to know the name and structure of an amino acid. So you will not be asked, hey, is this glycine? Is this alanine? So you do not need to know the actual name that goes with an amino acid. We'll talk about sort of how you need to know or the amino acids in just a second. But again, here, this is the ionized version. This is similar in all amino acids, this part of it. And these are our side groups. So if you have a hydrogen, it happens to be glycine. If you have a methyl group there, it's alanine, that's the side group. So again, you do not need to know specific names and structures. The way you need to know the amino acids is how it is broken up. And I believe it's broken up this way in your book, in the table as well, is you need to be able to recognize them as either being non-polar amino acid, polar, acidic, or basic. So if some amino acids are given to you in terms of their structure, you need to be able to look at them and classify them as one of these 4 ways. So non-polar is hydrophobic, which means it does not like water. It usually will contain just hydrocarbons, so carbons and hydrogens. So on our side group here, we pretty much see carbons and hydrogens. That should tell you that it's a non-polar amino acid. Polar amino acids are hydrophilic, which means loves water. They typically will contain polar or ionic side chains. So if we look over here, we have an OH group. That is a polar group, and it would be a polar amino acid. Acidic is also hydrophilic, which means it loves water, and it contains this group right here. If you remember, this is pretty much the carboxylic acid group. So it will contain a carboxylic acid group. It will be an acidic amino acid. And basic amino acids typically will contain a nitrogen containing group, a lot of times with a charge, something that's sort of based off of NH3, which is ammonia. Ammonia is a weak base. So those are typically what you will see on the side chain for your amino acids that are basic. Any questions on how to look for those 4 different classifications? And because they all contain the same part, which is in blue in these pictures, I think, you want to always look at the side group there to try to determine the differences. So just to kind of look at some of these examples, these are all non-polar amino acids. We have just a hydrogen, carbons and hydrogens, carbons and hydrogens. So again, this is what you kind of want to look at when you're trying to determine these things. I see a lot of carbons and hydrogens. These are going to be a non-polar amino acid. Polar amino acids, as we talked about, will have, like OH groups kind of in there. So I see an OH group, an OH group, an OH group. I see an SH group, which is very similar to an OH group. And here, these are amides, right? So we got some amides happening here. I see these type of groups. So these are the things that you want to kind of look at if you're given a picture of an amino acid to help you decide if this is, polar or non-polar. And again, as we talked about in terms of acidic and basic, you want to look for those, carboxylic acid group going to be acidic. And over here, again, our nitrogen sort of containing group with sort of a positive charge going to be something like ammonia, NH3, which is a base. Any questions on that there? So if we look at this, here's some pictures of amino acids. Oops, there we go. And if we want to sort of identify these as either being polar or non-polar, here, the actual side group is right here. It's an H and an H. So I'll just kind of get rid of that. And as you can see, since the side group is H, this is going to be non-polar. Here, our side group, I see an OH, which is a polar group. So that would tell me that this guy is going to be polar. So again, you don't have to remember names and structures, but if you're given the structure, you need to be able to kind of look at it and recognize it as one of those 4 sort of classifications. Any questions on how to do that? Okay, so hopefully they agree with me. That's good, they do. All right. So amino acids are chiral except for glycerin. And remember, chiral is the same thing we talked about with carbohydrates. It has 4 different groups attached. So this again is a carbon here, right in the middle. And kind of like carbohydrates, we can have L or D. And in this particular case, L or D refers to where the NH2 group is. So this guy is on the left, so it's L. This NH2 group's on the right, it is D. Same thing here, left and right, which would be D. So, you'll sometimes see amino acids labeled that way as well, L or D. So what we're looking at here is the nitrogen group on that chirocarbon, rather than what we did with carbohydrates when we looked at the OH group and where it is located at. So as I mentioned before, a lot of times we will deal with amino acids sort of in the ionized version, and that's what's referred to as a zwitterion. And that's basically what we're going to be doing is basically moving this H plus, if you will. we'll just pretend that way. That's not exactly how it happens, but we'll just kind of figure it that way. And we will end up with NH3 plus here and O minus here. So again, if somebody mentions draw the Zitteron version, or here's the Zitteron ion, what they're basically referring to is basically the ionized version of this amino acid. And it basically just means that instead of NH2, you get NH3 plus, and instead of OH on the other side, you get O minus. Any questions on that there? Okay. So let us do some more lecturing here. All right. So this slide, you don't have to worry about it. You could forget it. Not important. Still not important for us. Still not feeling the importance there. Still not feeling the importance. Still not feeling the importance. Not important. It's a good lecture. It's going good, I think. Not important either. This is going to be important, so we'll pick back up here. So back to semi-importance here. We're going to talk about what happens when we do put these amino acids together and they make certain bonds. So they do come together because they really do code for different proteins. And in order for them to code for different proteins, we need a big chain of amino acids to come together. And then when they come together, they form what are referred to as peptide bonds. And a peptide bond is really nothing more than the amide bond that we saw in organic chemistry. And surprisingly enough, it's a result of the removing of water. So this is the ionized version of an amino acid on one side. On the other side, we have another amino acid that looks something like this. Right. And basically what's going to happen is we're going to put these guys together by removing water. So we're going to take the O and we're going to take a couple of H's, and out will come water like here. And basically we will push this amino acid together with this amino acid, and we will make our amide bond, and that is our peptide bond here. And again, it's a result of basically pushing the nitrogen side of one amino acid together with the carboxylic acid side of another amino acid, removing water and pushing everybody together. And let's just take a look at an example of that. So if we took these two amino acids, serine and threonine, and that's what this means, we basically want to put it together in this order. So what we're going to do is take the O out of here. We're going to take two hydrogens out of here. And we're basically just going to push both of these guys together. And when we do that, what we will end up with is a bond that looks something like this as it comes through here. And here is our amide bond that forms as a result of that. And just so you can see, everything over here is exactly the same as it is over here. So absolutely nothing changes on that side of the amino acid. Everything that's piled on over here to start with is everything that is here to end with as well. Nothing changes. So we just make that peptide bond by really just pushing those guys together, and we form that amide bond, which again is referred to as a peptide bond. And that's really how amino acids basically stay together, are bound together, take out water, push together, makes that amide bond or that peptide bond. Any questions on that there? All right, so naming dipeptides, you do not have to worry about it, so don't worry about that slide. Don't worry about that slide. Don't worry about this slide. Don't worry about this slide. Don't worry about this slide. See, good lecture. Don't worry about this slide either. At some point, we may worry about something. Let's take a look here. And by the way, we'll just take a second look at this. But again, you can see when we put together all these amino acids, here's a amide bond, here's an amide bond, here's the amide bond. And again, that's all a peptide bond, basically, right? Peptide bond on all those. So it's just a picture of what we sort of been talking about. All right, so let's talk about this. So we'll talk about actually protein structure and what happens here. So there's a couple of types of protein structure. One is referred to as primary structure, and primary structure is basically the amino acid sequence. So it's all those amino acids that come together through peptide bonding that we just talked about. The order of those amino acids will basically code for different types of proteins. So again, if we want to look at our amino acids, one would be here, one would be here, one would be here, kind of broken up in that case. There's our 4 amino acids of where they would break up. Each of those where I drew the line is a peptide bond. Now, the primary sequence here, for example, just one change that occurs in that sequence gives you different proteins. So these are 2 different proteins, and there's only really two spots where they have different amino acids, but because they do have different amino acids in those spots, they do code for different proteins. And what ends up happening is you actually get obviously something that's different. So just the difference of one amino acid in a sequence can sort of, I don't want to say mess something up, but really change what it is. Here's insulin as well. And again, you can see everything here, all these amino acids is the primary sequence. They're all being held together by that peptide bond that we talked about. You will also see some of these guys, which is a bond that we also have seen before. It's a disulfide bond that we saw in organic chemistry with thiols. So when you have 2 thiol groups that come together, we take out the H and we get that disulfide bond. Cysteine is an example of that. That's an amino acid that actually has that SH group. So when you get a couple of cysteine amino acids near each other, they actually will go and form that disulfide bond. So you get some of those disulfide bonds happening. So general sequence here, primary sequence is the amino acid connection and backbone. There's also secondary structure of amino acids, and one such secondary structure is what is referred to as the alpha helix. Alpha helix, like DNA, is sort of that coiled affection or attraction that occurs, and that is result of hydrogen bonding happening on one amino acid's NH group and another's carbon oxygen group. So we have some hydrogen bonding happening here. But what ends up happening is it's an amino acid here and amino acid down the road that actually starts doing that bonding. So they're not next to each other, they're actually down the road. And that's what causes the whole sort of chain to do that alpha helix sort of coiling that occurs. And it's because they're actually hydrogen bonding down the road from each other, as you can kind of see here. And that causes that sort of coiling that occurs, which is referred to as the alpha helix. So this alpha helix is what is referred to as a secondary structure, result of hydrogen bonding occurring between amino acids down the road from each other, not near each other, but 4 or so down the road, causing the whole sort of chain basically to start to coil on each other. Another common type of secondary structure for a protein is one that is referred to as beta pleated sheets. And it's referred to as beta pleated sheets because essentially it's kind of like you take a piece of paper and you kind of fold it and then you open it up. And this is a result of amino acids basically hydrogen bonding side by side to each other. So they sort of hydrogen bond side by side as opposed to down the road from each other. And what ends up happening is we get this more pleated sheet type structure. And that's what we see in silk, for example. And here's an example of that. Again, this side to side hydrogen bonding between the oxygen and this carbon oxygen double bond and the hydrogen and the nitrogen bond, this side by side, given a more pleated sort of structure than a coiled structure that we see. Another secondary structure is a triple helix, and a triple helix consists of 3 alpha helixes together, making this sort of woven chain. And this is what we see a lot of things in, has a lot of glycine, proline in it. It's found in collagen and what we see in our skin. So just to sort of finish up here, we have a polypeptide chain that is held together by side-to-side interactions. That is 3, which is our poly beta pleated sheets. So side by side would be beta pleated sheets. Sequence of amino acids is our primary sequence. That's what that is. Corkscrew with amino acids. So that is our alpha helix. And lastly, our triple helix is all 3 of our polypeptide chains basically together. Any questions on that there? And just to finish up, there's also quaternary structure of a protein where we have a lot of interactions that occur. So when we get a lot of different sort of protein strands that come together, we get 4 different types of interactions that sort of occur. There's areas where we have, say, a sulfur and sulfur coming together, making our disulfide bond. And this is when we get, again, a lot of different chains sort of coming together. We also have areas where we get amino acids where they have nonpolar and nonpolar sort of side chains interacting. So we get those nonpolar interactions. We obviously will get some of our hydrogen bonding interactions occurring. And we'll also get some that will actually have some, I'll just draw it like this, ionic sort of interactions as well. And this happens when we just get a whole bunch of those polypeptide chains that, you know, when they do make a protein, there's more than one chain, they sort of all interact with each other. And we get a lot of these sort of interactions that occur between the different chains. Any questions on that? So for chapter 16, you need to know the general structure of amino acids. Again, not asked to draw it, but if you're given to you, you need to be able to recognize the different parts of an amino acid. You need to be able to, if the structure is given to you, classify the amino acid as polar, nonpolar, acidic, or basic. You would also need to know that the peptide bond is the amide bond that occurs as a result of a bond between the ionized version of one amino acid and the nitrogen part of another. So you need to recognize that bond as the peptide bond. You need to know that the primary sequence of a protein is the amino acid sequence, which codes for different proteins. You need to know the secondary structure of a protein as either being alpha helix, which is a result of hydrogen bonding between amino acids 4 from each other that causes the curling. You need to know the secondary structure of beta pleated sheets, which results from side-by-side hydrogen bonding of those amino acids. And you need to know here quaternary structure of a protein, which is when we get all these different strands of protein amino acid peptide chains together, that we can get interactions that results in disulfide bonds, nonpolar interactions, hydrogen bonding, and ionic interactions. Any questions from what you need to know from chapter 16? All right, believe it or not, that is it. That is all she wrote, I think. Yeah.